This is a worked problem from the AP Free Response Problem 3, Part D. Problem read, calculate the horizontal distance from the pipe that is reached by water exiting the pipe at 60 degrees from the level ground, assuming air resistance is negligible. Information given includes the water leaves the pipe at point B at a speed of 8.2 meters per second. As always, I start out by writing what I know and what I don't know. I do not know. I'm hunting for the horizontal or x distance. I know the velocity is 8.2 meters per second, and that's just the velocity, no component. And that the acceleration in the y direction is negative 9.8 meters per second squared. That was inferred, not directly stated. And that the acceleration in the x direction equals 0. Again, that was inferred, not directly stated, although they did mention that air resistance was negligible. To find the x distance that this water travels from here to here, so we're hunting for that x distance, I need to find the time in the air. The time in the air is the same for both the x and the y components. So we're going to use the y component to find the time that the water is in the air. Now, it was really tempting to use the time I'd found in Part C that I used to find maximum height, but there's a difficulty with that. The difficulty is that in Part C, the vertical velocity is straight up, okay? And it equals the velocity as the water is exiting the hose. But in Part D, the water's going out at 60 degrees, right here, this guy. Okay, so the vertical velocity is not the velocity that's leaving the hose. Notice here, and kind of what you'd expect from your intuition or from your common sense, that center spout goes up the highest. Then the next spout, the one with the next smallest angle, goes up not quite so high, and then that 60-degree one goes up not as high at all. So if it's not going up as high, it means it's not in the air as long. So we have to calculate the time in the air again. We're just going to look at the vertical components. Again, the acceleration, y direction, negative 9.8. The y velocity, if we're looking at this guy right here, that's the velocity of 8.2. But we just want the y component, which is this guy over here. The y component of the velocity is 8.2 meters per second times the sine of 60 degrees. This water spout goes all the way up to the top and then comes all the way back down. And so at this bottom point, when it's coming down, right here, the Vy, the downward velocity, by symmetry, is just negative 8.2 meters per second times the sine of 60 degrees. So that's the time it takes for the water to go all the way up and come all the way back down. The y velocity, assuming no air resistance, is equal but opposite to the y velocity at the starting point. But there's another place where we know what's happening with that y velocity, and that's right at the very top of the water. At the very top of the water spout, Vy is equal to 0. We could make that our final velocity, say that's Vyf, but realize that that's only the time it takes for the water to go up. So you're just finding the time to go up to that point. It's not the time to go up and back down. And of course, we got the equation Vyf, or Vf, equals Vi plus At. So you can work this either way. If you just want to calculate the time going up, which to be honest is what I tend to do, then I have the final velocity at that very top point is 0, so Vf is 0. The initial velocity is at 8.2 times sine of 60. The acceleration is negative 9.8. And I'm going to keep that symbol in there. The time going up is that unknown. And so you solve it, and the time going up is 0.7246 seconds. But remember, we're going to have to find eventually the time going up and down because we want that horizontal distance, and the water travels horizontally all the way. So not just as the water goes up to this point, but as it comes back down. But By symmetry, time up and down is just 2 times the time going up, so it's 1.449 seconds. You can solve for time that way, or you can, right at the very beginning, solve for the time going up and down. In that case, the final velocity is negative 8.2 times the sine of 60. So it means exact same magnitude, but the direction is different. It's going down now. And the initial velocity is still 8.2 times the sine of 60. Acceleration is still negative 9.8 meters per second squared. And this will give us all in one step the time it took for the water to go all the way up to the top and come all the way back down. And amazingly enough, you get the same time. T equals 1.449 seconds, which is a relief because you should get the same time because it doesn't matter how you work it. Now we'll look at the horizontal components. Horizontally, the acceleration is 0. Horizontally, the velocity is 8.2 times the cosine of 60. So now we're looking at that velocity in this direction, okay, the horizontal. And because the acceleration is 0, we can use the old equation v equals d over t. So we're going to plug in the x velocity. We're finding the x distance. And again, we need the time it took for the water to go all the way up to the top and come all the way back down. Rearranging it, I have x equals 8.2 times the cosine of 60 times 1.449 seconds, which gives us 5.94 meters, which is indeed the correct answer. Big difference between how I work it and the AP solution guide is the AP solution guide waits till the very end to plug in their numbers. So you guys weren't sure where the sine of 60 was coming in at. That's where it came in at. Thank you very much for your time.